Hi there. Here's a common situation. I've got a collection of text documents and an idea for a classification task. I've never done this task with this set of text documents, and I decide I want to use machine learning. To train a text classification model, I'll need to annotate some data, which is a very typical use case for interactive machine learning, or IML for short. Let's design an IML interface for my classification task. The most fundamental feature is displaying documents alongside annotation buttons so that I can assign labels to individual documents. As I label, I want an estimate of my model's performance, which is going to help me to feel like I'm making progress, to decide when to stop labeling, and to estimate how many more labels I'll need to get. Since I started from 0 labels, I have to estimate my model's performance on the labels I've created so far. I'll use leave one out cross-validation to compute whatever performance metrics I care about. In this talk, that'll be F1 score. But I can't display a performance estimate or even really get a feeling for the feasibility of the task until I have labeled documents in all of the classes. For binary tasks, if the percentage of documents with a positive label is low, common practical advice is to filter the data pool in some way to identify likely positive documents. Since we're talking text here, let's add a full text search feature that lets the user filter through the unlabeled documents to find positive examples. Finally, my IML interface automatically samples the documents for me to label. Rather than sampling randomly from the pool of unlabeled documents, an interface like this will use active learning methods to sample the batch of documents that will most improve the performance of the text classification model I'm training. Okay, well, we're not winning any design awards, but the interface is looking pretty reasonable. It's a simplified combination of several research prototypes that have appeared at IUI in the past. I can sit down with this interface and my classification task, start annotating documents, and an hour or two later, decide if the task seems feasible. But it was while trying to design an interface just like this that I became very confused. Active learning is appealing because it means I can achieve better model performance with less time spent using the IML interface. But this is the cold start setting. I don't have a separate labeled validation set, so does using active learning mean my model performance estimates will be biased or unreliable? I worry the same about searching for data to label, really convenient for exploring the dataset and finding uncommon positive examples, but since I'm implicitly sampling from a different distribution than the full dataset, I might be destroying my ability to reason about my model's generalization performance. In general, it seems like there might be a tension between the user experience of the modeler and the reasonable helpful features we want to put in the interface, and the performance characteristics of the model, trained from what are, effectively, different sampling distributions. Do you actually need to worry about this when designing IML interfaces? The purpose of our work is to show that yes, you need to worry about this. There is a real trade-off between boosting generalization performance and estimating that performance. This creates challenges related to user experience. The key takeaway is that you need to explicitly test the trade-offs between different desirable features, either through simulations on data from your domain, or, ideally, with actual users. We used simulation methods so that we could test a whole bunch of different sampling approaches and classification tasks at once. Let's try to formalize the problems we've been talking about by walking through an example. Here's what a simulated IML annotation session looks like. The interface randomly samples batches of 10 unlabeled documents and presents them to the user. Our simulated user then provides annotations for all 10 of the documents in the batch. For our experiments, we used a dataset of Amazon reviews, and consider here the task of identifying whether a review is written about a book or some other kind of product. The simulated user provides the ground truth label for each document without noise, so we completely omit labeling noise and data subjectivity from our simulations, letting us compare between experiments more fairly. Once a batch is labeled, we use cross-validation over all the existing labels to generate an estimate of how well our model is performing so far. By the way, the model we're using is logistic regression over pre-computed Roberta embeddings of our documents, which performs quite well but is also fast enough to train that it can be easily used to back an interactive interface. Since we're focusing on whether the classification task is feasible, we're just going to focus on the first 200 labels, what I refer to as early stage in the annotation process. Here's a visualization of the performance estimates a user would see after they labeled each batch. After 20 batches of 10 documents and a few fluctuations, they reached an estimated F1 score of 0.82. Because we're using simulations, we can go beyond the estimated model performance and also determine how biased the performance estimate actually is by using the model to make predictions on a held-out test set. I've added the true generalization performance as a solid blue line, and it looks like the model achieved a true performance of 0.83 after 200 labels, which is pretty close to our estimate. Now this example is from just one simulated run. We can compute 100 runs and take the mean to show the average run's true performance. That's what we're looking at now with 95% confidence intervals for the mean. For estimated performance, which I've added as a dashed line, we can see that cross-validation provides low bias estimates of performance, although on average our estimate is slightly pessimistic since we're holding out a single label that if included would improve the model's true generalization performance. But this approach is different from the IML interface we introduced earlier, which uses active learning rather than random sampling to construct each batch. Well, we're always going to have to use random sampling for the first batch, but once we've trained a model, we'll use the active learning method uncertainty sampling to identify the 10 documents that are closest to the model's current decision boundary. Uncertainty sampling is really widely used, in part because it's straightforward to implement and gives consistent generalization performance gains for models, and we can see that in practice. The true performance of models trained using 200 uncertainty sampled labels is almost 0.1 higher than the randomly sampled model. But uncertainty sampling violates cross-validation's assumptions. If we look at estimated performance as well, we see a troubling trend. As more data is labeled, the estimated performance actually decreases. If the interface reported these performance estimates to the user, they would falsely conclude their model performs more than 0.2 F1 lower than it actually does, which could be the difference between deciding to invest more annotation resources or scrapping the project as infeasible. And even if, in our particular use case, we don't care about accurate model performance estimates, we still might be dissatisfied with active learning methods that require already having a trained model. In our dataset, reviews are about books a quarter of the time, which is imbalanced but not extremely so. In more extreme cases, it can be hard to find positive examples, which will lead to a less effective classifier. We explored addressing this problem by seeding our classifier with positive labels by conducting a full-text search to filter the unlabeled pool. These are queries like book or plot, and they came from a survey of humans. By filtering the unlabeled pool before sampling our batch of 10 random documents, we end up with a higher proportion of positive labels, which lets us train a model right away and increase generalization performance. We can see that increase in our simulations when we replace that first batch of 10 random documents with a batch sampled randomly after a full-text search. But we're still paying for this improvement with increased bias in our performance estimate. But fortunately, it's not so bad here, actually. The estimate's bias starts high, but decreases over time as long as we can keep sampling randomly after our initial seed batch. Also, the bias is just a lot smaller when seed searching compared to using uncertainty sampling. Ongoing use of search beyond that first batch does substantially increase the bias of performance estimates. You can see the paper for those and other simulation results, including experiments we did with other active learning methods and combining active learning and random sampling in the same batches. Overall, I think these results are pretty heartening, since in my experience, a lot of early stage labeling starts with a small, non-random set of documents. And our simulation suggests that this probably won't hurt you, and if your classes are highly imbalanced, it might help you train a better model. The core thrust of our results is a trade-off between methods that will actually improve generalization performance and being able to give the modeler an accurate estimate of that performance. We have a few suggestions for modelers in the paper, but the more important implications are for designers of IML labeling systems. I'll end with these 4 guidelines. First, don't show the user a live estimate of model performance if it's likely to be inaccurate. And similarly, discourage search and non-random sampling if model performance estimates are important to the user. I personally like the suggestion by Emily Wall and colleagues to offer literal prompts to encourage or discourage particular kinds of labeling or exploration throughout the annotation process. Third, you can encourage search for positive examples early in the annotation process to increase generalization performance. Not only is this unlikely to hurt true performance, there's good qualitative evidence that people value this kind of opportunity to explore the data, and it's going to help people reshape their understanding of the annotation task. Finally, I do encourage use of non-random sampling when true performance is the primary or only objective. Our results suggest that in the absence of domain shift or a need to estimate model performance, it will help to use active learning methods. Thanks for listening. I did this work while I was an intern on Vanessa Murdock's team at Amazon. Huge thanks to Max Harper and CJ Lee for acting as my direct mentors during this internship. Please feel free to email me if you have any thoughts or questions. I'd love to know if our results resonate with your experiences training interactive models or designing IML labeling systems.